doing, I owe 2 people Seaport. No, because that class wants to do it now. I'm like, do you realize how hard that was to carry all those heavy heroes with all the iced teas? Like, a lot. It was a lot. And I didn't even realize, I wasn't thinking. I was just like, oh, okay. Like, ditzy, like, oh, yeah, I got it for you. And then I'm like, oh my God, this is so heavy. And how am I going to get in the, oh yeah. Is that what I do? Disclaimer. Okay. Yeah, I'm on the mic. You guys want to say hello? This is only for you, Sabrina. Is that where she is? Visiting at college? Say hello. Hi. All right, this one's for you, Sabrina. All right. Shout out. I know. I always feel like that. Okay, so which variable represents the explanatory variable? Which one, guys? Q. Where's Q? Wait, guys, this. We're right here. Y hat equals A plus BX. It's a line. No. No, the explanatory variable. X. X. And which variable represents the response? Yeah, well, y. In this case, y hat is when you actually figure out the line. Now, what does A represent here? Y-intercept, yep. And B is the slope. Excellent. And, oh, beautiful. Are A and B statistics or parameters? Statistics, yes. It's right on that. Yeah. So, yes. Let me put this down. Okay. So, moving right along. Now, remember, oh, this is this is in the textbook, this question. And I'll just sum it up for you, what the question's about. They took these infants and no, they didn't make them smoke. They took rubber bands and no, they snapped them on their feet. And I'm not kidding. You can read it. No, wait, no. I'm on the mic. Okay. So wait, hold on. I can give you a shout out. Let me just finish my thing. Okay. So they snap the rubber bands and then they want to see how loudly they cry, and how loud they cry, their cry count determines their IQ. Bizarre. I don't know. Yeah. So that, if you want to read in the blue textbook, it's example 15.1. All right, Jonathan, you're on the mic. You're on the mic. Oh, he wanted to tell us the story. Okay. Yeah. Or it's just me and no, it's this. It's this screen, but me writing. Yeah. All right. So remember what? No, absolutely not. I don't want them to. All right, so now we have, remember this was the computer output, and we had to be able to read this. So and remember I said when we did this section, I'm like, don't worry about this, don't worry about this. Remember? And I only said focus on, now you have to worry about it. So remember, they usually give you, they don't always give you the equation. That's usually not what happens. But remember, cry count here is the explanatory. And IQ, don't do that, guys. Come on. You said you would only use it. Stop. IQ was cry count. I mean, sorry. You guys just distracted me. Is the Y, the response. Okay, so remember, next to cry count was your slope. So this right here was your slope. That's your slope. This would be what? The constant coefficient, y-intercept, good. This was my y-intercept. Okay? Okay, now the r squared, again, we talked about how that says if you have a good model. And the higher the number is to 100%, or 1 if they put it as a decimal, means that you have a good model. Is this a good model? No. Did you draw on that? Who did that? You drew on my stress ball?
I'll get you a new one if you really don't like it. I agree. I thought it was squeezing anything.
Let me see when you squeeze it. All right, anyway, so this is this one I may only have to give to Sabrina. All right, so this is not a good, it's an indicator, not a good model. Okay, now how would you get the r from the r squared? Yeah, so if you take the square root of 0.207, that gives you r. Now remember, when they give you r squared, what? Because that's a decimal. Like when you take, yeah. So, give me that now.
No, he's making it happen. I'll make it happen.
See, I was trying to be nice to you, John.
You are nice, but it's just
No, I was trying to be nice to you. Okay, anyway, remember that when you take the square root of this, you have to determine the sign based on the slope. Remember that? So if it was a positive slope, then your r would be positive. If this obviously, because it's squared, is going to be positive, but your slope was negative, then you'd have to make your r negative. So whatever the number that comes out to be. And then the other thing on this computer output that we talked about when we did this unit was the s. Do you remember what the s was? It is a standard deviation of the Yes, what were those called? Yes, yes. So this was the standard deviation of the residuals. And the residuals are your error, right? So basically this is your prediction error. So this is a prediction error. Oops, I want to. Okay, so now even you can see we usually ignore this part. Not anymore. We have to dive into this. Now, this really should now make sense to you, because before you were like, I don't even know, but what distribution do you think they use? T. Yep. And what do you think the P is? The P value. Now in here, do you see that right here? It's not the top one, it's the bottom one. Yeah. You don't, I just know that, well, actually, wait a minute. I know. It could be the top. But either.
Then why would it be a p-value of 0?
No, because look at your test statistic. Because if your test statistic is 10, that's how standard deviations, that would be 0. That would be your test statistic. Yes, which is why your p-value is so low. Usually it's the bottom one. I don't know why they circled that, but usually it's the bottom one. And then this is your standard error, which we'll go through. But so it all should now look like you recognize what's going on there. When I told you ignore it, you had no idea. That's actually not what normally happens, though. Like that doesn't really look like this one. It usually looks like the other one. So, all right. So now this is an applet, so you can get a sense of what's going on. So this is just, I could like reset this to be any slope. So let's make any slope. 1. It's the keyboard. Okay. It does go fast. All right, so now you can, so remember the idea was you have a lot of points, and you're trying to find the least squared regression line. So what happens is, does it say draw a line anywhere? I don't see that. You don't have to read it, you just have to see it. So now look, if I drew samples, right? That is, like, so, actually, let me redo this. Let me keep it as is. Let me put it as 0 so you can get the idea here. And then we can play with it. All right, so the idea is with inference that you have everybody in the population, right? Well, like you're trying to get everybody in the population. So with inference for all these dots is everybody in the population. And so what happens is you're trying to find the least squared regression line that would come from sampling the population. So you draw a sample, and then based on that one sample, that's the least squared regression line. And then you draw another sample. Different samples are going to produce different lines. And so you can just keep sampling. And you see how you have all those different lines? So when we're doing inference for regression, you're basically trying to figure out, well, what's the true regression line? Do you see where this is going? Yeah. So you're trying to figure out which one of these lines is actually the true least squared regression line. And that's the idea here. So let's keep going. All right, so now these are the conditions. And again, these are usually satisfied. So write that down. Usually satisfied. They usually say conditions have been met. Why? Because then you would have to enter in all the data. And usually that's too time consuming for the AP, so they'll say that. Because you wouldn't be able to satisfy these conditions for inference of a confidence interval or trying to figure out what the true slope is if these are not met. So it says the sample must be randomly selected. Oh, that's a big shocker, right? What's the number one condition? Random. All right. Now the scatter plot should be approximately linear. Another one that's not a shocker. Right? You want to know that you're dealing with data that's approximately linear. There should be no apparent pattern in the residual plot. And this is a kind of a cool way to do it. Hold on. To ensure standard deviation of y is the same for all standard deviations of x. I could show you on the next page what that looks like. And now the distribution of the residual should be approximately normal. This can be checked by a histogram, dot plot, stem plot, or a normal probability plot. So unless you have the data, you can't check for these conditions. So again, that's why they say normally that the conditions have been met. So in like the textbook, the way they write it, you have our goal is to study or predict the behavior of y for any given values of x. So repeated responses y are independent of each other, hence why you want random data. The mean response, now we go from this, which is the least squared regression line from the sample, to this. And what do you think that is? Yes, this is the least squared the true least squared regression line. And this would be from the population. So, like we said before, A and B are statistics. And then here, your alpha and your beta would be not statistics, but parameters. Excellent. Yes. So this would represent the true slope. And this would be the true y-intercept. So we're trying to figure that out. So going back up, it says the mean response mu of y has a straight line relationship with x. The slope of b and y are unknown parameters. The standard deviation of y, call it sigma, is the same value for all values of x. the value of sigma is unknown. Hence, if the value of sigma is unknown, what's my distribution? T. And how many degrees of freedom you think it has? Usually you would think n minus 1, but how many variables are there? 2. So in a t distribution for regression, it's always n minus 2 degrees of freedom because there's 2 variables. No, there's not a weird formula. It's just the sample size minus 2. Why? Because they only made that weird one because that is when they were comparing 2 populations. This you have 1 population. And the reason why they did it for comparing is because when you compare, it's not a true t distribution, which is why they came up with that funky formula. And then it says for any fixed value of x, the response y varies according to a normal distribution, which is this picture shown here. So this is saying like for any value of x, so if you had this x1, this x2, this x3, when you plug in an x and you get a y, that the responses would be normally distributed. This is not like a really big deal, but that's what this condition is talking about right there. Yeah. All right, so good news, usually you don't have to do these unless they give you the, no, really, they usually say it's met. So now, no, I have 2 more minutes. I'm going to keep going, right? So now, the confidence interval for the slope beta of the true regression line is this. So B is the slope of the sample. That's what B is because it's little b. If it was big B beta, then that would be the slope of the population. I feel like I said beta though. I shouldn't have said beta. I don't know if I did. We already talked about that it's a T star. And then SEB is standard error of the slope. Standard error of slope. Now, a lot of times, yes, you are usually given a computer output that calculates all this, and you don't have to calculate anything. You just have to know where to find it on the computer output. So now, SEB is S, which S is that standard deviation of the residuals. Over the change in Y. And we'll pick up where, change in X. We'll pick up on Monday with this. We have Monday, Tuesday, right? Yes. And then I'm probably going to have a video on frappies. Yeah. What? It's fine, Bryce. You should have asked me, though.